Hello. Today we want to discuss briefly some of the main features of the graphs of polynomial functions. The graph of a polynomial function is said to be continuous because it has no breaks, holes, or gaps. Also, the graph of a polynomial function has only smooth, rounded turns, not sharp turns. Intuitively, what we mean by the concept of a continuous function is a function whose graph can be traced without lifting your pencil off the paper. A polynomial function f of x equal to a sub n times x to the power n plus a sub n minus 1, x to the n minus 1, and so forth, plus a sub 1x plus a sub 0, is said to have degree n and has at most n real zeros and at most n minus 1 turning points, or relative minima or relative maxima. The a's are constant coefficients that are real numbers, and the variable x has the highest exponent in any one term of n, and that's why we say this is degree n for this particular polynomial. Its graph is going to intersect the x-axis in at most n places, and it's going to have at most, as we said, n minus 1 relative minima or relative maxima. Since the graph of the polynomial function has a limited number of turning points, eventually, as x approaches minus infinity or as x approaches infinity, the left tail and the right tail of the graph must rise or fall without bound. If the graph has changed directions as the maximum number of times that it can and cannot change directions anymore, then that makes logical sense that on the end it would have to either keep going toward infinity or going toward minus infinity. What characteristics of the equation for f of x will influence the behavior of these tails of the graph? Well, two things: whether the lead coefficient is positive or negative, and whether the degree of the polynomial is even or odd. Specifically, we can use the following test to determine the end behavior of the graph of a polynomial function. We call this the leading coefficient test. If the polynomial is even degree and it has a lead coefficient that's positive, then as x goes to minus infinity on the left or as x goes toward positive infinity on the right, in both cases, the y value is going to be approaching positive infinity. Both the left and right tail of the graph will be going up. If the polynomial is even degree but has a lead coefficient that's negative, then both as x approaches minus infinity on the left and as x approaches positive infinity on the right, the y value in both cases is going to be approaching negative infinity. Both the left and right tail of the graph will be going down. If the polynomial is odd degree and has a lead coefficient that's positive, on the left, as x approaches minus infinity, y will be approaching minus infinity as well. And on the right, as x approaches infinity, y will be approaching infinity. If the polynomial has an odd degree and its lead coefficient is negative, then on the left, as x approaches negative infinity, y will approach positive infinity. And on the right, as x approaches positive infinity, y will be approaching negative infinity. If you notice, when there is an even degree, either both the tails are going up or both are going down. If the polynomial has an odd degree, the tails are going in opposite directions. To gain an intuitive understanding of the reason that this test works the way that it does, consider these examples. Here is a polynomial function y equals 10x to the fourth plus 5x cubed minus 3x squared plus 2x plus 1. The highest exponent on the variable in any one term is 4, so this polynomial has degree 4, an even degree. Its lead coefficient, the coefficient of the highest power of x, is 10. So we have an even degree, 4, and a positive lead coefficient, positive 10. I could rewrite the equation for this as y equals x to the 4th times, in parentheses, 10 plus 5 over x minus 3 over x squared plus 2 over x cubed plus 1 over x to the 4th. Think about it. If you multiplied this out, 10x to the 4th is the first term. X to the 4th multiplied by 5 over x. Well, x to the 4th divided by x is x cubed, and then it's times this 5. And then subtract the 3 over x squared times the x to the 4th outside the parentheses, because x to the 4th divided by x squared is x squared, plus 2 over x cubed. Again, x to the 4th divided by x cubed is x times this 2. And then finally, x to the 4th times 1 over x to the 4th is just 1. So you can see that this second line is algebraically equivalent to the line above it. Why did I write it like this? Because now you can see that as x approaches either positive infinity or minus infinity, 5 over x minus 3 over x squared plus 2 over x cubed plus 1 over x to the 4th are going to be approaching 0. Think about it. If x were 10 million, 5 divided by 10 million is very, very tiny. Or if x were negative 10 million, 5 divided by negative 10 million is also close to 0. So as x approaches plus or minus infinity, y is going to be getting closer and closer to simply 10x to the 4th. Now, if x is approaching positive infinity or negative infinity, x to an even power is going to be approaching positive infinity, times 10 is still going to be approaching positive infinity. So we see in this case that both the left and right tail have a y value that is approaching infinity. Both tails are going up. What about an even degree with a negative lead coefficient? Here we have a polynomial, and we changed the initial coefficient from 10 to minus 10. We kept 4 as our even degree in this example. I factored out the x to the 4th, just as I did in the previous example. And now look, as x approaches plus or minus infinity, y is going to be approaching minus 10x to the 4th, because all of these other terms are approaching 0. Now, as x approaches either positive or minus infinity, x to the 4th would be approaching positive infinity because it's an even power, but a positive large number multiplied by negative 10 means it's going to be approaching negative infinity. So in this case, with an even degree and negative lead coefficient, the y value on both ends of the graph is approaching minus infinity. Both tails will be going down. What about an odd degree with a positive lead coefficient? Let's say that y equals 7x to the 5th plus 3x to the 4th minus 2x cubed plus 5x squared plus x plus 5. We have an odd degree, this is degree 5, and a positive lead coefficient 7. Here I factored out x to the 5th, and what remained was 7 plus 3 over x minus 2 over x squared plus 5 over x cubed plus 1 over x to the 4th plus 5 over x to the 5th. If you multiply this out and distribute the x to the 5th, you will see that you get the original polynomial. It's algebraically equivalent. Now, as x approaches minus infinity, y is going to be approaching just 7x to the 5th. All of these other terms would be approaching 0 as x approaches minus infinity. If x is a very large negative number like negative 10 million, x to the fifth is also going to be negative because it's raised to an odd power. And this large negative number times 7 is going to be approaching minus infinity. If x approaches positive infinity, then as y approaches 7x to the fifth, that is also going to be approaching positive infinity. So in this case, the left tail would be going down and the right tail would be going up. As our final example, suppose we have an odd degree with a negative lead coefficient. This time I changed the lead coefficient from 7 to minus 7, but we still have a polynomial of odd degree, degree 5. Factored out the x to the fifth once again, and what you see here in parentheses would be what is left. If you distribute the x to the fifth and multiply through, you'll see that you get the original polynomial. Let's see what happens as x approaches minus infinity. The y would be approaching minus 7x to the fifth because all of these other terms would be approaching 0. And if x is a large negative number raised to an odd power, that's going to be negative. But a negative times negative 7 would be a positive number, a very large positive number approaching infinity. On the other hand, as x approaches positive infinity, x to the fifth would approach positive infinity, and a positive times the negative 7 would be negative toward negative infinity. So here, the left tail is going up and the right tail is going down. Another thing to consider about a polynomial function are its real zeros. If f is a polynomial function and a is a real number, then the following statements are equivalent. X equals a is a 0 of the function f, or x equal to a is a solution of the polynomial equation when you set f of x equal to 0, or x minus a is a factor of the polynomial f of x, or the point a0 is an x-intercept of the graph of f. Be familiar with all of these terms and understand that this essentially is 4 different ways of saying the same thing or making statements that are mathematically equivalent, provided that a is a real number. Now we want to talk about what are called repeated zeros. The following pertains to a polynomial function f of x. If you have a factor x minus a raised to an exponent of k, where k is greater than 1, we say that a is a repeated 0 of multiplicity k. If the k is odd, the graph is going to cross the x-axis at x equals a, and if k is even, the graph is going to touch the x-axis at x equals a. What do we mean by that? I think, again, a picture is worth 1,000 words. Let's look at 2 examples. The red graph here is f of x equal to x plus 2 raised to the 4th power. For the factor x plus 2, minus 2 is the 0 of that factor, because minus 2 plus 2 is 0. The k here is even, it's positive 4. So this would be a multiplicity of 4 for the 0, negative 2. The red graph is the graph of this function, and you can see that it is just touching the x-axis at negative 2. The graph remains on the same side of the x-axis to the left and the right of the 0. The blue graph, g of x equal to x minus 4 cubed. For this polynomial, 4 is the 0 because 4 substituted for the x gives a 0 here inside the parentheses. So we're going to have an x-intercept of 4, 0. The multiplicity, k, is equal to 3, an odd multiplicity. And you can see that at this x-intercept, this graph does cross the x-axis at this 0 because it does have odd multiplicity. There is an important theorem for polynomial functions called the intermediate value theorem. This says let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, in other words, one is positive and the other negative, then there's at least one value of c between a and b for which f of c equals 0. Here is a picture that I think it makes this very easy to understand intuitively. Here is f of a. It's below the x-axis. And here is f of b above the x-axis. What this theorem is saying is that because polynomial functions are continuous, there's no way that I can continuously trace the graph from this point below the x-axis to this point above the x-axis without crossing the x-axis at least once between those 2 points. So you could see in this graph that I have crossed the x-axis right here. It's an intermediate value, intermediate meaning between. The value of the function at a is negative, the value of the function at b is positive. So there has to be a value of an x-coordinate c between a and b where f of c is 0. 0 is between a negative number and a positive number. Here is an example problem to use some of the things that we've just been talking about. Looking at this graph, suppose you were asked to come up with a possible equation for the graph. There could possibly be more than one correct answer, but we can look at some features of this graph and know some requirements of our equation. First of all, since both of the tails, both the left tail and the right tail, are going toward positive infinity, we know that this function has to have an even degree and a positive lead coefficient. The x-intercepts here are at -1, where it's touching the axis, 0 where it's crossing the x-axis, and 2 where it's crossing the x-axis. Because it's touching the x-axis at -1, -1 has to have even multiplicity. Because it's crossing the x-axis at 0, 0 has odd multiplicity. And because it's crossing the x-axis at 2, 2 has odd multiplicity. The factor associated with -1 would be x minus -1 or x plus 1. Since it has to have even multiplicity, I put an exponent of 2 on that factor. The factor associated with a 0 would be x minus 0, which is just x. Since it has to have odd multiplicity, I left it to have an understood exponent of 1. And the factor associated with the 0 of 2 would be x minus 2. And since it had to have odd multiplicity, I assigned an exponent of 3 to that factor. If you notice, as the graph crosses the x-axis at 2, the shape of the graph in that neighborhood looks a little bit like a cubic function. What is the degree of my f of x? This would be x cubed times x squared, which is x to the 5th, times another x, which would be x to the 6th. So this polynomial function has degree 6, which is an even degree, and its lead coefficient would be just +1. So it has a positive lead coefficient. Here is another example where we have a graph and we want to come up with a possible equation. We are assuming in this graph that the right tail would be going up toward positive infinity and the left tail would continue going down toward negative infinity. So that tells me that it should have an odd degree with a positive lead coefficient. The x-intercept of -13 should lead me to a factor of x minus -13 or x plus 13. It's crossing the x-axis there, so it's odd multiplicity. The x-intercept of -5 leads to a factor of x minus 5 or x plus 5, again with odd multiplicity. The x-intercept of 0 gives rise to a factor x minus 0 or just x. And again, it's crossing the x-axis there. The x-intercept of 4 gives rise to a factor of x minus 4. There, it's touching the x-axis, so that should have even multiplicity. I gave it an exponent of 2. The x-intercept of 7 leads to a factor of x minus 7 with odd multiplicity because it's crossing the x-axis. Finally, the x-intercept of 10 would lead to a factor of x minus 10 to an odd multiplicity because it is crossing the x-axis there. What is the degree of g of x? X times x times x squared times x times another x. If you add that up, your highest power of x is going to be x to the 1, 2, 3, 4, 5, 6, 7, x to the 7th power, which is odd degree, as we said it should have. And if you notice, how many turning points does this graph have? 1, 2, 3, 4, 5, 6. The degree is 7. The maximum number of turning points would be 7 minus 1 or 6. And surely enough, this graph does have 6 turning points, 6 relative maximums or minimums. Hopefully this helps you appreciate the graphs of polynomial functions and some of their main features. And you will have fun graphing some polynomials for practice problems.